Okay, so we've learned quite a lot. We built a single particle theory. We've discovered that the single particle theory is in fact sick. Particles in our theory can move faster than light, and that spoils relativistic causality. So in this theory, the windows might shatter today because the bomb is going to explode tomorrow. Well, that doesn't make any sense. It's not sensible, so this is not a good theory. But what we should ask ourselves is, where did we make the mistake? I mean, we haven't assumed very much. In equation 1, we assumed there was a momentum operator and that its eigenstates provide a basis for Hilbert space. That looks like a perfectly good assumption. We also assumed some dynamics, the form of the Hamiltonian. Well, this by relativity looks like a perfectly reasonable Hamiltonian to make. And then finally, we said we could measure the position of a particle, and that's the only input. So one of these statements must be wrong. In fact, the statement that is wrong, quite remarkably, is that we cannot measure the position of a particle. In quantum field theory, it is impossible to measure the position of a particle. So let me try to explain to you why that's the case. So we are going to imagine that we have a photon, and we're going to try to give a recipe by which you could actually measure the position of the photon. So let's say our particle is a photon, and let's trap our photon. So it's trapped in a container whose walls are mirrors. So here is our container, and the walls of this container are mirrors, so that, the photon, every time it strikes a wall, it's just reflected off the wall, but it's captured inside this container. And then how are we going to measure the position of this particle? Well, let's imagine that one of these walls, it's also a mirror, but it can be moved. So I could squash this wall, and I could keep decreasing the volume of this container. And in that way, I trap the photon in a smaller and smaller region. That way, I know with better and better precision what its position is. So this is what I'm going to take as my experiment to actually measure the position of the photon. And let's try to see what will happen when I do this experiment. Well, let's say initially, so we've got a very big container. Let me plot the wave function psi of x, okay? So here is x, here is psi of x. And what I might imagine is the container is very big, the particles very spread out, so it's some sort of a very broad wave packet, and I don't really know where the particle is. I can also ask myself, well, what does the momentum space wave function look like? And remember, the key formula to keep in mind here is delta p, delta x must be greater than or equal to h bar over 2. We must always respect the Heisenberg uncertainty relation. And initially, our particle is very spread out in x. We don't know where it is. So delta x is large, and that means delta p can be small. So here, delta x is very large. So it's perfectly okay to have a delta p which is small. No problem with that. So we might have a wave packet that's tightly peaked around zero momentum in momentum space. So now we start to push our plunger and we localize our particle more and more. After doing this for a while, what we might find, so let's use a different color. Let's say localize particle, and we do this by pushing plunger. Okay, by pushing, let me say the wall. So I'll push the wall of the container, make the container, the volume of the container smaller and smaller, and in the end, the particle will be well localized. So then, if I look at psi of x as a function of x, and let me now draw this in red. So what's happened is the wave function is becoming narrowly peaked. So what this means is delta x has decreased. And what that means for the momentum space wave function, if delta x has decreased, now if we look at psi of p, delta p, so in fact, let me change that color. Let me make it blue. Delta p has increased. Now, why did delta p increase? Delta p has increased because when I was pushing this plunger, the photon was bouncing against the wall and it was creating some pressure. And when I push that plunger, the photon bounces against the wall and it picks up some momentum. I have to do some work against the photon to push the plunger. The photon's producing a pressure. I have to do some work against that pressure, and the photon moves faster and faster. This is just like when you squash a gas into a container, it gets hot because all of the particles inside the container are moving faster and faster. Here I'm pushing the plunger. When I'm pushing the plunger, I'm actually exerting a force on the photon. Its momentum is increasing, and the photon is getting more and more momentum. Now, previously, when the particle wasn't very localized, at this point over here in momentum space, there was no chance of detecting the particle with such a high momentum. Now, in fact, there is a chance to catch the photon with a very high momentum. So there's a non-zero probability to find the photon with a big value for momentum. But if it's got a very big momentum, this implies it will have a very big value for the energy. But now I want to remind you, we're working in relativity. And remember, in relativity, E is equal to mc squared. So if you squash this container enough, you will give the momentum, you will give the photon such a large amount of momentum, such a large amount of energy that it can actually pair produce. That photon can produce, say, an electron-positron pair together with the photon. And if you keep squashing more, you give all of the particles in the container a lot of energy, and they will all start to pair produce even more. And long before you've managed to localize the photon, you've got a whole soup of multi-particles inside that container. And this is exactly what we've neglected, those multi-particle effects. So basically, when you try to localize your particle to measure its position, you give the particle more and more energy. There's no way that that cannot happen because that is dictated by the uncertainty principle. By decreasing delta x, you have to increase delta p. And there'll be some components of the wave function that have such a large energy that you'll get pair production. So long before you manage to localize the single particle, you've got a multi-particle soup. And because of that, it's just not possible to measure the position of a particle. No operational definition that you come up with to measure the position of the particle will allow you to do so. So in quantum field theory, the position of the particle is not something that you can measure. Well, if we can't measure positions, what can we measure? In the next chapter, we are going to argue that the natural thing to measure in a theory with special relativity and quantum mechanics are fields, and we'll introduce the idea of quantum fields. We'll build those fields, we'll figure out how to work with them, and we'll show all of the problems that we had of our single particle theory are solved by working with fields.